In this video, we're going to talk about change of parameter and arc length. Okay, so let's start with a definition. A curve that is represented by a vector-valued function r of t is said to be smoothly parametrized. Or we could say r of t is a smooth function of t if, first of all, the r is differentiable. So the r prime of t exists, okay, for each t. But not only does r prime of t exist, r prime of t is continuous. And the derivative is never zero for any allowable value of t. Okay, so what does this mean? Well, geometrically, this means that a smoothly parametrized curve can have no abrupt changes in direction as the parameter increases. Okay, for example, you couldn't have a sharp corner in it, or it couldn't change direction and trace back over itself, even though the curve itself might appear to be smooth. So let's look at a couple examples, then I'll draw a picture here and we'll see what I mean here. So let's determine just kind of algebraically here, or analytically, whether these vector-valued functions are smooth or not. Okay, now part A is this r of t is cosine ti plus sine tj plus tk. Now actually the graph of this is a circular helix. Okay, but is it smooth? Is this a smooth function of t, or is this smoothly parametrized? Well, let's check. Does the derivative exist? Well, r prime of t is going to be, well, we take the derivative within each of the components, negative sine t cosine t 1. So notice r prime of t exists for all values of t, and it's continuous because each of these component functions is continuous. And also, there's no value of t that would make this be 0, 0, 0. Okay, in fact, the third coordinate could never be 0, it's 1. You could find a value of t that makes sine of t 0, for example, if t is 0 or pi or something. Or if t is pi halves or 3 pi halves or something, it would make this 0. But there's no value of t that'll make all three of these be simultaneously 0. So this is a smoothly parametrized curve here, okay, or a smooth curve. Now what about the second curve here? Now that was a curve in 3 space. This one is just a curve in the plane, right? There's no k coordinate here. We have r of t equals t squared I plus t cubed j. And you think, oh my goodness, these are just polynomials. Of course this is going to be smoothly parametrized. Well, not so fast here, right? What is r prime of t? Well, r prime of t is 2t comma 3t squared, right? We take the derivative within each of these components. And notice that 2t and 3t squared, right, they both exist, right? The derivative exists, but not only that, they're also continuous. But the one other thing we have to check, though, is could this be equal to the 0 vector, 0, 0, for some value of t? And notice there is a value of t that makes this the 0 vector, namely when t is 0 itself. So when t is 0, we get the 0, comma 0, right, which is the 0 vector. By the way, this is a bold 0 right here, the 0 vector. So notice this is not smoothly parametrized. Now you might think, well, what about the graph of this? Is the graph of this have any sharp corners? Well, it turns out it does have a sharp corner. Okay, the graph of this, and actually I have it in Desmos here a little bit better. Okay, the graph of this in Desmos is here. Now this is going from -1 to 2. If we let t go from -2 to +2, let's say, we'll get this. Okay, we could go from -3 to 3 or whatever. But if you go -infinity to infinity, you get this thing that traces out the curve in this way. Okay, but notice when t is 0, we actually get right here and there's a sharp corner, right? So notice this is not a smooth curve. Okay, so this is not smoothly parametrized. So we did have an issue when t equals 0. Now that's not the only way that you can have an issue with the curve not being smooth because that the derivative is 0. You could have the curve giving a sharp corner like that, or you could have a nice smooth curve, like this little piece of a curve, if it's being traced out one way and then it kind of abruptly changes and traces back upon itself, and then maybe it abruptly changes again to trace this way. That would also not be smoothly parametrized because you're still getting these sort of sharp corners, even though you're not actually seeing the sharp corners because you're going straight along. So to be smoothly parametrized means that each of the components have to be differentiable. And not only that, the derivatives themselves have to be continuous. So we have 2t and 3t squared. That's fine. But also, the derivative can never be the 0 vector for any allowable value of t. Okay, so that's what it means to be a smooth curve or smoothly parametrized. Okay, now let's talk about arc length. Recall that the arc length of the parametric curve x equals x of t, y equals y of t, where t runs from a to b, is given by this formula. So when we talked about arc length for parametric equations, we had this. Well, you can do the same thing in 3 space, right? If you have x equals x of t, y equals y of t, z equals z of t, you have some curve winding around in 3 space. You want to know how long is that curve from where it starts at t equals a to where it ends at t equals b. How long is that curve? Well, it's given by this formula, right? Notice it's a generalization of this formula. The arc length is integral from a to b of the square root of dx dt squared plus dy dt squared plus dz dt squared. Okay, dt. Okay, so let's, but notice, isn't this, well, there's a different way that we can write this. We can rewrite these formulas in vector form. So if r of t is x of t, y of t, z of t, right? I've written in the IJK notation. Notice what's dr dt. Now, dr dt is another way of saying r prime of t. So this is dr dt or r prime of t, however you want to write it. Notice it's dx dt I plus dy dt j plus dz dt k. Okay, or you could put this in the bracket notation. Now, what's the norm of this vector? Well, the norm would be the square root of this thing squared plus this thing squared plus this thing squared. And that's exactly what we have here. But notice that's just this. Okay, so the arc length of a parametric curve is actually the integral from a to b of the norm of dr dt. Okay, dt. So that's really our theorem right here. We have the following theorem. C is the graph in 2 space or 3 space of a smooth vector valued function r of t. Then its arc length, the arc length of this curve, which we'll call L, from t equals a to t equals b is given by this formula. Okay, so that's just another way of writing the formula that we had above. Okay, so let's do an example. Find the arc length of the circular helix x equals cosine t, y equals sine t, z equals t. Okay, by the way, notice in this formula you need to have a smooth vector valued function. Okay, otherwise the curve could maybe retrace itself and you'd have issues with that. Okay, but find the arc length of this circular helix from t equals 0 to t equals pi. So notice this circular helix winds around and it keeps winding around. When t is 0, we're right here at the point really 1, 0, 0. Okay, when t is equal to pi, we're way on the opposite side of that cylinder, sort of halfway around on the other side of that cylinder. And so I think we would be at the point -1, 0, pi. Okay, but the question is, what is the length of this curve? So I've kind of traced it out here in red. How long is that curve there? Okay, well, let's actually work out the details here. So r of t is cosine t sine t t. So dr dt, or r prime of t, is negative sine t cosine t 1, right? We just take the derivatives component-wise. And so the arc length from a to b, so this is our formula here, is the norm of dr dt, dt. But remember, the norm of dr dt is going to be the square root of this thing squared plus this thing squared plus this thing squared. And that's what we've written here. And by the way, we're plugging in 0 and a, or 0 and pi for a and b. Okay, but notice minus sine t squared is really just positive sine squared t, and this would be positive cosine squared t, but sine squared plus cosine squared is just 1. So what we have is the square root of 1 plus 1, which is really the square root of 2. Now, we don't have to write this as 2 to the 1/2 power and then make that to the 3/2 over 3/2, because notice this is just a constant. Okay, we don't have the square root of t dt, it's the square root of 2 dt. That's just a constant. So the integral of a constant is just that constant times t, right? Like the integral of 5 would be 5t. So the integral of the square root of 2 would be the square root of 2t, evaluated from 0 to pi. And so if we plug in pi for t and then subtract what we get when we plug in 0 for t, we end up getting the square root of 2 times pi, okay, which is about 4.443 units. Okay, so that's the length of that curve. Okay, by the way, if you had projected this curve down into the xy plane, right, if this curve just lied down here in the xy plane, so it, of course, would be shorter if it were just down here in the xy plane, you'd basically be getting a semicircle. And you'd ask, what's the length of that semicircle? And I think the length of that semicircle would actually just be pi. Okay, if you work out the details, it'd be a circle of radius 1, which would have a circumference of 2 pi, right? 2 pi r, but r is 1. So half of that circle would have a length of pi. Well, notice, since this is winding up, rather than just staying down in the xy plane, it should be longer. It should be longer than pi. And notice it is longer than pi. It's the square root of 2 times pi. It's about 1.414 times pi. Okay, so that's the length of that curve. Okay, now is it possible that 2 different vector valued functions could give the same curve? So you have 2 different, like, r of t's. Could they give you the same curve? Okay, either in 2 space or 3 space. And it turns out the answer is yes. And in that case, we'd say that the curve is parameterized differently by the 2 functions. Okay, so let's look at an example of this. So the curve, consider these vector valued functions. So r1 of t is cosine t sine t. So this is just going to be in the plane here. We're not looking at a circular helix. We're actually just looking at a circle here, or a portion of a circle, a semicircle. So we're going to let r1 of t be cosine t sine t and let t run from 0 to pi. So actually it's going to trace out this curve here. Okay, when t is 0, we're going to be at 1 comma 0. And t is pi over 2, we're going to be here. And then when t is pi, we're going to be way over here. Okay, now r2 of t is going to be the same thing, only instead of doing cosine t sine t, we're going to do cosine 2t sine 2t. But the crazy thing is it's going to trace out the same curve, and it kind of makes sense that it would trace out the same curve. And by the way, though, we're letting t run from 0 to pi halves. So this traces out the exact same curve, this exact same semicircle. Now it traces it out a little more quickly because t is only going from 0 to pi halves, but when t is 0, we're here. When t is pi over 4, we're there. When t is pi halves, we're there. So it actually traces it out more quickly because t only runs from 0 to pi halves rather than 0 to pi. Okay, but they trace out the same curve. Okay, so we have two different parameterizations of the same curve. Notice that we can always do this actually by replacing all the t's in some vector valued function with, say, 2t, okay, or some function of t, so maybe t cubed plus 1 or something like that. Replace all the t's with that. Okay, now notice that these give the same curve in 2 space, a half circle, but r2 is traced twice as quickly as r1. In fact, let's look at the derivatives of these functions at the derivative of r1 at pi over 2 and the derivative of r2 at pi over 4. Now notice these are the same point here. So r1 of pi over 2, if you plug in pi over 2 in for r1, you're going to get 1 comma 0. Actually, that should say 0 comma 1. And r2 of pi over 4, that should say 0 comma 1 as well. I put 1 0, but I really meant 0 comma 1. Okay, that's right here. Okay, so these should say 0 comma 1. Okay, but what's the tangent line there at 0 comma 1? Okay, what's the tangent line? So if we plug in, if we want to find the tangent, these tangent vectors here, let's take the derivative. So r1 prime of t would be, well, the derivative of cosine t sine t would be minus sine t cosine t. And then if we plug in pi over 2, we're going to get minus sine of pi over 2 comma cosine of pi over 2. And that would be, well, sine of pi over 2 is 1 and cosine of pi over 2 is 0. We get minus 1, 0. So if we look at the tangent vector right here to this curve, r1 of t, then we get this minus 1 comma 0. So notice it goes to the left 0 and up and, or left 1 and up and down 0. Okay, so there's the derivative of r1 at pi over 2. Now what's the derivative of r2 at pi over 4? Now again, r2 at pi over 4 gets us to the same point, 0 comma 1. But what we get is, this time, is when we take the derivatives of r2, the derivative of cosine of 2t would be minus sine of 2t times 2. And the derivative of sine of 2t would be cosine of 2t times 2. And this time, if we plug in the pi over 4, it turns out what we end up getting is minus 2 comma 0. You can check the details there, but notice this is minus 2 comma 0, so we don't get the same tangent vector. The tangent vector is actually twice as long, and that actually has to do with the fact that this is being traced out twice as quickly. All the tangent vectors, the tangent vectors that you get when you do r prime of t, or r1 prime or r2 prime, will be twice as long. Okay, but notice they're facing the same direction. They're still both tangent vectors. Okay. So we have two different curves, we have, it's really the same curve being traced out by two different vector valued functions. Okay, so this curve is parameterized differently, okay, for r1 and for r2. Okay, now it's often useful, especially for theoretical purposes, to parameterize a curve using arc length. Okay, and to parameterize a curve using arc length, what that means is that when you look at where the curve is when t equals 0, where it is when t is 1, when t is 2, the distance between these 2 points is always 1. So you're moving along at a constant speed of 1 unit per second. If you have a curve where that's taking place, then that curve is said to be parameterized by arc length. Now, if you have a curve that's going faster than that, or slower than that, or maybe sometimes it's speeding up and then it kind of slows down and then it speeds up and then it slows down, then that wouldn't be parameterized by arc length. Okay, a curve is parameterized by arc length basically if it's always moving along at a rate of 1 unit per second. Okay, if you think of t as being in seconds. Okay, in fact, what does that really mean? Well, it means that the length of dr dt would always be 1. Okay, now sometimes they use the letter s for an arc length parameter instead of t. So here's a theorem. If c is the graph of a smooth vector valued function r of s in 2 space or 3 space, and again we're using s here instead of t, where s is an arc length parameter, then for every value of s, the tangent vector to c has length, well, it always have a length of 1. Okay, because the length of that tangent vector essentially has to do with the speed of how fast the curve is being traced out. Now, by the way, you could parameterize a curve by arc length a couple different ways. I just let t be 0, start here, and then that determines where the curve is for all the other values of t. But you could have let t equal 0 correspond to different points. And in fact, you could even have the curve being traced in the opposite direction. Okay, and it could still be parameterized by arc length. Okay, but to be parameterized by arc length means it's always moving at this constant rate of 1 unit per second. Okay, and again, we often use the letter s when we're parameterizing by arc length instead of t. In fact, the converse of the theorem is also true. A smooth vector valued function is parameterized by arc length if and only if the norm of its derivative is 1 for every input. Okay, so arc length parameterizations are important, especially for theoretical purposes, and we'll look at this will come into play some in the next section.